All right, here's a video on how to solve problems with masses on pulleys in physics. Let's suppose there's actually some friction in this one. So we'll say that coefficient of friction will be 0.25. So there's two ways to do these problems. First way, we could just do our standard force diagrams. So I'll do a force diagram for this 8 kilogram object. So there's some tension pulling to the right. It's going to be pulling to the right, so that means there's going to be friction to the left. Friction always opposes the motion. There'll be a normal force and some weight. So that's the 8 gram mass. Then there's the 6 gram mass, and it looks like this. Tension pulling up and force of gravity pulling down. We'll start with this one because this we can kind of figure out because we know the mass, we know Fg, so we can solve for T. So what I'm going to say is if this thing's moving down, if there's a net force acting down, then I would say that F net is equal to Fg minus T. And we could say that Ma is equal to actually I'm going to go mg is, let's just say for make it a bit easier, G is 10 newtons per kilogram. So that means mg in this one will be 6 times 10 equals to 60 newtons. Okay, so I'm going to say that I'm going to call it m6a is equal to 60 minus t. And that's pretty much all we can do for that one. Let's look at this one then. We know that vertically this mass is balanced. It's sliding horizontally on the table. So we have here then force of friction is mu mg in this case. So that's equal to mu times, so that's, we'll call that 0.25 times 8 times 10. So 1/4 of 8 is 2 times, so that's 20 newtons. Okay, so if this thing is sliding to the right, then we'd say that F net for this one is equal to T minus force of friction. So in this one we have M8A is equal plus 20 is equal to T. So now we have two equations and two unknowns. The A in both of these is the same, and the T in both of these is the same. So I'm going to rearrange this. I'm going to say that T is equal to 60 minus, I'll just call this 6A, 6 being the kilograms. And this, I can just say that that's 8 kilograms. So these two are equal. So 8A plus 20 is equal to 60 minus 6A. And now we can solve for A. So I'll move the 6 over here. So this is going to be 14A. And then I'll subtract 20 from both sides. So that's 40. And I get A is equal to 40 divided by 14. And that is 2.86 meters per second squared. Once you have that, we could use either one of these equations. We could use this one or this one to solve for the tension in the rope. So that's how you can do that using straight up force diagrams. The other way to kind of do it is this idea that this pulley is redirecting forces. So in some ways we could say that we could draw, maybe I'll use a different color. Oops. We could also maybe say that we have 8 kilogram block, 6 kilogram block, and it's being pulled to the right by Fg of the 6, and it's being pulled to the left by force of friction of the 8. And there is string between the two, but really that string's just holding them together. So really it's kind of like there's that one big mass. So if we think of it that way, and we say, okay, it's moving in this direction, it's accelerating in that direction, I should say, we could go F net is equal to FG6 minus FF8. The net force in this case is comprised of both the 6 kilograms and the 8 kilograms times the acceleration, and that's equal to, we already did the FG at 60 and this is 20. So in this case we get A is equal to 40 divided by 14, and you see we get the exact same answer. So really, you can answer this either way. This is kind of like it's just a higher level of way, or bigger kind of picture way of thinking about it. Whereas this is like using our tried and true, draw really good force diagrams, get our F-net equations from our force diagrams, and then solve for the unknowns. Okay, here's a more difficult one. Let's suppose we have a mass that's actually on an incline. And there's a bit of friction here. Let's say there's a friction of 0.01. So the 2 kilogram mass is going to want to pull everything down and to the right. The 8 kilogram mass is going to want to go like this. And I think we just have to take a guess as to what's going to happen. I think I'm going to take a guess it's actually going to go this way because the 8 is so much bigger than the 2. So let's draw some diagrams here. So this is the 8. It has a normal force like that, mg like this, and if it's going to the right, or sorry, if it's going down, there'll be a friction this way, and there'll be a tension that way. So that's our full force diagram. This mg will have 2 components. It has like the normal force. This would be like, let me write that differently. This is like the perpendicular component of the mg, and this is the parallel component of the mg. So I'm going to redraw this whole block again. I'm going to do it with a new coordinate system. So I'm going to go FF, T, N for normal force, FG perpendicular, and FG parallel. Okay, so that fully describes that block. If it's sliding down in this direction, then we're going to have F net equals FG parallel minus tension minus force or friction. We can calculate FG, which means we can get these components, and we can get the force of friction. So let's do that. Okay, so this is the 50 degrees. So we have FG perpendicular is equal to, so mg cos 50. I'm going to use 10 for g again. So we got 80, 50 cos. So that's 51.42. FG parallel is mg sine 50. So that will be a little bit more. Oops. That's 61.28. Okay. This is also equal to the normal force. So we can actually calculate force of friction now. It's going to be mu n. So that's going to be 0.1 times 51.42. So that's 5.142 newtons. Okay, so we know most of these things here. F net is going to be the 8 times the acceleration is equal to 61.28 minus 5.142 minus t. Okay, that's okay. Let's solve for t. I'm going to, what do I do here? So it's going to be 8a. No, sorry. I'm going to subtract one from the other there. So 61. So that's 56.14. So I'm going to move t to the left side. So t is equal to, what did I say it was? 56.14 minus 8a. Okay, so that's one equation. Now we got to deal with the other mass, the 2 kilogram mass. So the 2 kilogram mass is much simpler. T and mg. So I was saying that I think it's going to be moving up. This one's going to be moving up. So I'd say F net is equal to T minus mg. So F net is 2a, excuse me, 2a equals T minus, and this is 2 times 10. So in this case, I have 2a plus 20 equals t. So now, once again, I have two equations, two unknowns. And so in other words, this bit here is going to be equal to that. So let's write that down. 2a plus 20 equals 56.14 minus 8a. Okay, so I'll move the 8a over here to the left, so that's going to become 10a. And I'll subtract 20 from that side, so this becomes 36.14. And a is 3.61 meters per second squared. So there you go. That's how you can do that one. Now, this one you can also do like as a system as well. Very much like the other one. You still have to calculate like these values here, the 51.42, the 61.28, the 5.142. That's still the case. Once you have those, you can kind of think of it like this. Here's the 8. There's the 2. There's 2 times g here. There's F parallel there. And then there's also a little bit of force of friction there. The tension is internal to the thing. It's what's holding it all together. It doesn't really matter for this calculation. So this would be like F net is equal to FG parallel minus FF minus 2 times 10. In this case, F parallel is, F net is M8 plus M6 times A equals 61.28 minus 5.142 minus 20. So A is equal to all that. Divided by 8 plus 2. And I'm pretty sure we're going to get the same answer as before. So 61.28. 5.142 subtract 20, divide by 10, 3.61. Same. Oops. There you go. And then once again, you could use an acceleration in this equation to get the tension. Alrighty, good luck.